Yeah, thank you very much. Georg, you're wonderful. First of all. Yeah, so let me take you a little bit with chemistry to where I had the pleasure to go, and maybe I can show you what was possible. So I'm proud to be an alumni here of this wonderful place, and I hope that you will see that it got me to the places where I never dreamed that I could be able to. But with some good education, you know, things are possible. Actually, so what happens now? Actually, I have a riddle. I love chemistry, but would I, for an element, build a huge artwork more than 100 meters tall and found a society with more than 100 million members? And at the end of my talk, I will try to give you an answer. Now, this is the chemistry building at the Leibniz University, where I have also my office in, and it is the oldest building in Germany which has just been built for chemistry and ever used that way. Of course, there are older ones, but the president has a bigger one, yeah. And it was actually the kings of England were the kings of Hannover for 123 years until women, Queen Victoria came, so from 1714 till 1837. But you know, we are named after Gottfried Wilhelm Leibniz, and he said you can do everything out of nothing, or one is enough, just one is enough. And he created these binary numbers. This is his own writing. We have the World Heritage in Hannover on that. These are more than 200,000 letters in his own handwriting, 70% in Latin, 20 in French, and 10 in German. And we took his own writing as the logo for the university. Maybe you know probably much better when you use the integral sign. That is his notation which he used, and the other one developed by Newton was never extended to this grade. So everybody's using the Leibniz notation in the world who is really doing math and not just using the fluctuation method by Newton. But no, this is a different story. Now I want to go to some story of this young fellow. He did in his PhD thesis something which changed the world, at least for me a bit. Rudolf Mössbauer found in 1958 the recoilless nuclear resonance absorption of gamma radiation. And you know, what's the big deal about it? Well, like when you shoot with a Mössbauer gun, you have no recoil. So this sounds like as if Newton's third law, action is reaction, doesn't work. And yes, you have a quantum mechanical workaround. And he got immediately 3 years after the Nobel Prize. And the question is why? Because this method was so precise that he could observe relativistic effects at the velocity which is much smaller than the speed of light. And so here now, so when I have my sample here, do a Mössbauer experiment and cool it down by 20 degrees, I get a relativistic shift. And that's amazing. And that's why this was the first possibility to really directly observe these effects. And the way he did it and the instruments he had is amazing. So he used some toys from a toy store to get to his Nobel Prize. So when I heard this story about building up the institute here, it reminded me what Mössbauer has told me during his work. But it was finally awarded with the Nobel Prize. And actually, I asked the Nobel Committee already several times to tell me why. Because some people say his PhD father, Meyer Leibniz, that he should have shared the prize. But when I asked him this question, he said, no. And I said, but how did you convince him not to be on that paper for which you have been awarded with the Nobel Prize? And he said, I did it physically. I put pressure on him. So Mössbauer, yeah, it was, ask me in the coffee break, I'll tell you more. Actually, the hyperfine interaction is what we see. This is the electric monopole, the magnetic dipole, the electric quadrupole. These are the three interactions which we can nicely describe when doing a Mössbauer effect. And one of the most important elements is the iron 57. So what we need is, when we have a radioactive source, we get only one energy, but we need a plus and minus energy to get a spectra. So for this, we just add the Doppler velocity, which means we just move the source and then we get the velocity on top of this photon and guiding us to a spectrum when we do an absorption measurement. And yeah, I don't want to go into details. Ask me, if you want to know more, ask me afterwards, because I want to tell more stories than going too deep on some single things. So this is a regular setup of a MIMOS boron. This is the one, the miniaturized MIMOS boron spectrometer, what we have, and I have one with me. So after this presentation, you have a chance to see it. So this is the original size of this miniaturized MIMOS boron spectrometer, of which we have 3 on the Mars. On the planet Mars. NASA was so kind to take them there, so we could not resist. So you see, so this is it. So we have 4 detectors, pin detectors. There's the source which is moving to get the Doppler energy, and we hit the sample, and then the energy comes back. We did a big mistake actually during the construction of it, because we put the reference channel in to really control the drive to do a checkout on the fly. And this checkout on the fly almost killed us on flying to the Mars, because we were the only ones having a checkout on the fly in the rocket. The others didn't have it. So during the fly, we did the checkout and we had problems. Our line waves got broken like crazy. And all the other instruments had no checkout on the fly. But what was told to the press was, all instruments work fine, except the MIMOS boron. But was the only one having a checkout on the fly. So we got really annoyed, and and I still remember the day when I was in the mission control center, and then you hear the worker, and then they said, okay, we switch off the pump. This was approaching Mars, and I went to the technician and said, is it true you had a pump running next to a MIMOS boron? The pump will disturb our signal. We are measuring so fine things, a vibration will kill our whole signal. So I understand why it didn't work the whole time. 7 months, I'm going from Earth to the Mars. And he said, I asked him, why didn't you tell me this? Then we would have never told to the press that we are able to measure this. And he said, you didn't have the security clearance for that. So wonderful, really wonderful. So, and this, after landing on the Mars, this is already the robotic arm, and here you see it on the rock where we do the measurements, or on the soil. And this is actually the first meteorite ever discovered outside of Earth. So the first Martian meteorite, the meteorite which hit the Mars, and we could find him. It's actually some chemisite-based material, so it has a lot of iron, so it was easy for us to measure. So we could measure in transmission, which looked like this, or in emission on the Mars, since we cannot take the sample easily, so we do mostly these backscattering mode measurements. Now this miniaturized MIMOS boron started in 1990 with Professor Kankeleit in Darmstadt. So he was actually a colleague of MIMOS boron. Like, so they worked together under Meyer Leibniz, and Kankeleit had the idea to use as a drive, use this speaker more or less, instead of this rotational plates, which MIMOS boron has used. And this is the setup which was then further on used. And both went to the Jet Propulsion Laboratory. No, actually, this is adjacent to the California Institute of Technology. So MIMOS boron was awarded when he was postdoc at the California Institute of Technology with Kankeleit, and they both came back and got some nice professorships, the one in Darmstadt and the other one in Munich. And one of his students was Gösta Klingenhofer. So the first version of this device was bigger, and it was supposed to go with a Russian mission. And in 1990, there was a spring in the world, and so the Iron Curtain was more or less disappearing, and so it was possible to do such kind of missions. And actually, I have to say, both attempts unfortunately failed. Then we had another attempt which failed in 2011 with the Russians, and right now we are not allowed anymore to collaborate with them. So it is with the Chinese. We are not allowed anymore, so they told me that I could be considered a spy if I only talk to them on that subject. But they desperately want this device, I can tell you. I have offers but I don't want to go to jail. It's not worth it. So when we moved completely the development of this device to Hannover, and that's where I'm doing it now. So I was younger than here. This is Gösta Klingelhofer, and that's me a little bit younger. So when we were working on this in the Jet Propulsion Laboratory in Pasadena, and yeah, that's how it looks like. And for instance, some developments, when we have these pin detectors, they are quite broad in energy resolution, and we can use the silicium drift detectors, and then we can even resolve different signals and get much more information out of our sample. And when we have the energy, so we go for 2D so that we get all the transitions, and we can get emissions and transmissions really at the same time with the same detector, which is quite amazing for such kind of things. Also, sometimes, you know, this kind of Prussian blue compound. Oh, sorry, it's German. So this Prussian blue compound, I did it here for TV to show it that we can do it even from food additives. These E-number compounds, and actually, I had a nice talking to some of these TV cooks. He said, "I never use any of these E numbers," and I said, "Don't lie or stop breathing. Oxygen has an E number. You just consume it next to me, and you tell me you don't consume it. Don't lie to me, please be serious." And that was, I didn't make friends at the time, but at least I made my point. So yes, and the Prussian blue actually from this 1703 until 1963, the Mössbauer spectroscopy was the one who could resolve that when you use the iron 3 and the iron 2 cyanides and get this Prussian blue, then there was another synthesis. We use iron 2 and the iron 3 cyanides, and you get this so-called Turnbull's blue. And what you see is you actually get the very same things. You get the signals for the two, and then you get the third signal. The third signal is when the electron is jumping from one to the other. So basically these two pigments, which have been for hundreds of years considered to be very different, are more or less the same because of that. And then one day I had the pleasure here to do some measurements on these grid compounds. They go from high spin to low spin, and that was with the Nobel Prize winner Jean-Marie Lehn. He received the Nobel Prize for the supramolecular structures, and this was one of them. Actually, what I don't like so much from the organic point of view, that he considers coordination chemistry to be a part of the supramolecular subgroup. So it's for him, we are not doing, our complexes are not molecules for him, but I can live with it as long as they are switching nicely here. And actually I could show him that for the first time we got this kind of compounds switching, and he believed that they would not be possible. And we had a nice picture from Kandinsky, and this was just an anniversary. It could be like integration, a ligand with the iron, and then it forms these tetramers, and only if the ligand is on, it could go to low spin. So as if Kandinsky had almost 100 years before an idea about that. Now, this is a lovely instrument. You have a nuclear source, and you have the ESRF, the synchrotron, and at this one we also did some switching, but at that time with hard X-rays, and we could for the first time close a gap here to switch these things at a really atomic resolution. But I have no time to explain you any details. What I really want to do instead is we used such kind of switches actually to implement them into this device, and that was actually one additional contribution for this mission. Now, what's so interesting about Mars and Earth? So now you see we have like 1,000 millibars. On Mars you have only 10 millibars right now, which means you're actually below the triple point of water, so you won't have liquid water. Why? Was there liquid water in the past, or it was not possible, obviously, because the pressure is too low? Well, I will answer the question in a minute. And how important is it? Was there water, liquid water in the past? And there were some speculation on this, and we could give a solid proof with our mission on that answer. And the answer is there was water, and there was ocean-like amounts of water. And why did it change, and what will happen to Earth considering these things? Now, when you look at iron, iron is playing an important role. When it is inside the Earth, you have the zero in the center of the Earth, and then the liquid state, some silicates, olivine and pyroxene, and when they come out, they can, depending on the conditions, can oxidize in different ways. You can have green rust, for instance. Green rust is the rust which actually was the one stopping Napoleon entering Great Britain, because the green rust corrosion was so fast, faster than building up the constructions Napoleon needed for doing that. But that's a different story. Now here's a different way, so you get different byproducts, hematite, goethite, machimite, and when you see these different products, you can read the geological textbooks. And of course you have some living species, they have some magnetites or other types of magnetic compounds inside, like this magnetotactica bacteria. And like goethite is one of this which still has the hydrogen in, and I will just explain you in a minute what is the important thing about it. Now this is the rover Spirit and Opportunity. Actually we first called them rover 1 and 2, and then NASA said, this is boring, you should rename it. This is not a really creative way, so please come up with something better. So the scientists came up with A and B. And A was 2 and B was 1. And then they said, okay, we ask our kids, and then there was like an 8-year-old girl, and then she was 9 already, and she shook hands on TV with the NASA boss, and she said, with the right spirit, we'll have the opportunity. And since then, we called them Spirit and Opportunity. So there is a competition every time they send such a mission, and and here is this is the IDD, this robotic arm, and these two devices. I'm responsible now for these two devices. There's this miniaturized MERSPER and some elemental analysis, alpha, proton, X-ray spectrometer. So these are the spots. Usually the landings are more like in the equator, not in the polar region. There are some others in the polar region. So we had 3 missions. These 3 missions took our device to Mars so far, and we had some really outstanding achievements. But what did MERSPER say when we did fly to the Mars and we had problems with this obvious, as we know then, vibrations? He said, it's so sensitive, I'm afraid it will not work, but I hope that I'm wrong. And I can say, he would be proud that he was wrong, because it worked very well. And here's the very first spectra on the Mars, and we did a real mistake, because we put this spectra to the press, and this spectra shows you a lot of iron 2 content and some iron 3. The green is iron 3, the others are like, this is olivine, this is pyroxene, and this is some iron 3 content. And you see the majority is actually iron 2, which you would not expect, because the Mars is so red, so this is oxidized, yeah? But it's only a very small layer, and the majority is still not oxidized there. And when we, the by story of this, when we put this on the NASA TV, because NASA said, oh, you have a nice, it's midnight now, but in next morning we will have a press conference and you show this spectra, and so you're working not only 12 hours, you're working longer. The Mars has 24 hours plus something, which is almost 25 hours. So when I start working today at midnight, then it's tomorrow at 1, and the next day at 2. So every day I refresh my jet lag for 1 hour, which I call the universal jet lag. Which is, so we had here a real spectrum. We put the energy scale down here and the intensity, and somebody took it and submitted a paper to Nature magazine the next day. And then they wanted to convince us to do some negotiations with them or whatever, and we said, that is not, we are not going to do any press conference anymore if this is the result. But we decided to change from Mickey Mouse chemistry. We omitted the scale, simply. And then there were even some other guys who tried to submit such things. So this was the crater landing on Mars. And here's the robotic arm, the IDT, just doing measurements. Here are the tracks of the rover ongoing there. And you see one spot, we looked at them, they're these little spherules, and we could nicely measure them, background and below. And you see this magnetic things, so these, they're called moss berries, but they are really consisting of magnetite. And this was actually the very important compound nobody had on the list. This is a ceroside, so when you have some pyrite and it decays, then this signal is one of the biggest one you find in minerals. So it was very clear, and the important thing is you still have the hydrogen in. That means this thing was not grown in a melt. So when you have iron and you have an iron oxide in a melt, then you get such spherules like this. But if you have the hydrogen still in, then the hydrogen has a high diffusion potential. That means if you heat it up above 800 degrees, it disappears. And only then you can get such compounds. So we know exactly now how the water on Mars, and this must have been grown in water, was. It was right to lead to the formation of this ceroside, which means pH 2 to 4, which is a little bit sulfates. You have sulfates in. So it was quite acidic and yeah, maybe it was not so tasty, but you know. And we found it all over this place here. So when we were walking, and we did walk for quite a distance. Now the Mars was a blue planet, and everywhere where we find this ceroside was water. So that was a clear proof of it. So, but now what happened, and why did it disappear, and why did the pressure go below 10 millibars so that liquid water is not stable anymore? So actually, the thing is, the volcanoes, they can blow out gases and increase the pressure. So the volcanoes did it, because the mass of the Mars is much smaller than the Earth. The diameter is half of it, and the G 9.81 is 3.6. So it's simply not enough. But the volcanoes, they could do that. And the magnetic field both stopped. And that was a problem for the Mars. And it can also happen to Earth. And there are things how we can avoid it. Now here is one of these NASA press conference where I could show the first spectra of the Opportunity rover, which was the second mission, and here we see already these magnetic parts, and this is Steve Quires, the scientific lead. He's actually the successor of Carl Sagan. If you have heard about Carl Sagan, was one of the main fathers who actually managed to get the first mission to the Mars in the 70s, the Viking missions, and we were able to publish these things nicely, and even the Science magazine awarded us with the Breakthrough of the Year award because of finding the proof, the direct chemical proof on the soil that there was liquid water in the past. And actually here you see the tracks on the Mars when this rover is moving, and he signed the letter which got us the money for the mission when he was vice president under Clinton, and Al Gore just lost faintly against Bush the election, but that's a different story. But he was very, very kind. Actually, just for getting my passport here at NASA would have got me, well, taking it to Europe by accident, they told me 10 years of prison in the US. So it's also in the US it's not so easy. 10 years, yeah, but I did not forget it so far. So I told them actually I made a joke out of it. I said, oh, does that imply that we have the better techniques in Europe to forge such things, or otherwise you would not be worried about it. But anyway, yes, and we achieved something which was great. We could go with this rover for the first time a distance longer, so like this Eagle crater where we landed over this Endeavour crater and Victoria crater, and to this Endeavour crater here, we reached a distance which is longer than a marathon. And for this, every one of us got a medal for the first marathon outside of Earth. And here you see the tracks of the robot. You can have a look afterwards if you're interested. Now, what is the future? Well, we plan to go there with a hexacopter and land with these things. We have some tests already. And actually, the European Space Agency has selected us with the label Outstanding, which is actually one above excellent. Yeah, I didn't know that there is one above excellent, but excellent would have been nice already. But now we got that and we took it. So we are on the list, and there are several missions which I hope that we can join in the near future, and we'll see. But we know already from the Apollo missions, that sample which we're taking down, and I had the pleasure to meet some of these guys who have been on the moon, which is really wonderful, like Harrison Schmitt, which is the only geoscientist who worked there. And so here we have minerals, we know what we can see, and besides that, there is the Artemis mission, which is going to land soon, and there is a plan for the South Polar region to have a station on the moon, moon, and this station on the moon also needs power supply and other things. And one of these power supply things is actually like a hydrogen storage, and for this hydrogen storage, for this hydrogen storage, we are also working on, but that's a different subject, which I maybe address afterwards. Now we try, it's time for a MIMOS to go to the moon. And this, Now we also had other samples, for instance, just in the night from the 20th to the 21st of January this year, close to Berlin in Riebeck, one meteorite came down, and this meteorite actually turned out to be older than the moon. So it was coming from the times before the Earth was the Earth as we know it now. It was the pre-Earth, and there was no moon at that time, because the moon was formed when some impact came to the Earth, and then there was a separation, and that's why the moon has a lot of similarities with Earth, but we can clearly distinguish moon material from Earth material. And if you don't trust me, I have a sample from the moon here. So if you want to see a small piece, but a real piece. And and some of these meteorites, and you see there are some patterns. This pattern arises when you cool it down 1 degree in a million years, which the steel production on Earth has never made so far. And and actually there's a guy who is coming, and there are always such guys coming, and one is Apophis, and this Apophis actually at first looked like he would come in 2068, but then they found out it's much closer than that this year, and he will come on the Friday, the 13th of April in 2029, and he will be quite close to Earth, so he will be in the 10% distance from the Earth to the moon. He will pass by. And we will be in the pole position in Europe. We will be able to see it nicely. So Europe and Africa and South America, and there are several missions scheduled to go there, like Ramses and Apophis. So there's the Hera mission, which just started to observe some of these asteroids, but we say this is now a chance, because it just changed this year, so we didn't know, we couldn't plan ahead to really go there, or there was no mission, so we had to adapt some of these missions, and we're on the list. Let's see whether we can join, but at least the NASA has their own mission, and they want to take samples so we could get hand of the samples, and the JAXA, the Japanese Space Agency, they successfully returned samples from such meteorites, and in the Falcon missions, the so-called Hayabusa 1 and 2 missions, which he did. Well, somebody said something about some art, and I will not talk too much about it. We are writing a book on this story, but we found out that actually my brother found such a picture in a garage, and the leading experts said this is garbage. So I said, if it's garbage, I can do science on it, and it looks nice. I want to do some science. And we have already published something like 800 pages PhD thesis and some papers, but we write another book on it, and we have found a lot of evidence, and our space device was quite useful for this. And actually, so some people claim, and we found a lot of similarities. What this is actually confirming that this picture has something got to do with Gustav Klimt, but not the top layer, because some not so scientifically talented guy overpainted the picture after the Second World War with some titanium oxide pigments, which were discovered after the Second World War, and Klimt passed away in 1918, so it was not Klimt. But the layer below, we can date back to the 1879, 1880, which clearly fits to Klimt and his time. And Gustav Klimt, there's the Japanese version, and this was worth more than 100 million euros when he was on auction, the most expensive painter at this time. Now it's a Da Vinci or Hyako Yonjuroku Okuen, if you want. Probably the rate has changed. Didn't update it. So, but we did the measurements on it, and we could see clearly what is below. So to see that really the top layer, we took off the top layer to free the original from it, and it's really a very interesting story. And there's a lot of press, even some TV documentations have been made about that, and some more are in progress. Actually, I even got to the parliament with this device. So they invited me because there was supposed to be some Roman field, which the textbooks say the Romans have never been to Hanover, but we found a lot of evidence which are clearly from Romans, and analytics can really help. Now this is the Japanese, the JAXA Hayabusa 1 mission. They shipped it with this rocket. They have this H rocket, and this is Hayabusa 2 landing on another meteorite, and they are very interesting in returning samples. Now this was my president, and he sometimes invited me to show something to the students, like 1,000 students in a room, and the professor has to say hello, and I say hello to the student, and the students like it, or yes. But then the students, they complained, this is not fair, so I said, okay, now this is me upside down, yeah, and the student is throwing me. So I teach these things. It's true. I have some black belts in this modern form. After 1868, the Japanese had the modern style techniques, which is called Aikido, and actually this is the lost metal, which is actually iron. But I don't like this writing, because the old way of writing before the Second World War, it means the king of the metals, and I love iron so much that I would call it the king of the metals. And if you this means, for instance, Kinsho, which means gold medal, and I really got a gold medal in the competitions of this. But this is the Japanese Daito Ryo Aikichu Jutsu Hombu. So this is the samurai style before 1868, and I have the highest graduation in this one, which you can find among the Austrians or Germans, for instance. But that's a different story. And yeah, I'm very happy that I've been awarded such honorary PhD. They told me, the German Chemical Society told me I'm the number 4 at my university among the chemists since foundation, since 1831. And the last one before me was 1991. And yeah, I want to say thanks, and thank you very much. And now I come, yeah, this is part of my group, not all in front of the building. And of course, they are the ones who did most of the work, because I mainly don't have the time. So now here's the riddle, and probably you have already found out what is the favorite element. The element is actually the iron, and this artwork is the atomium in Brussels. It is nothing else than the room temperature structure of iron, and actually the iron was the one. You had, after the First World War, the League of Nations didn't work. The Second World War came. The United Nations didn't help. There are still wars going on in the world. But in Europe, the foundation of the European Union gave the longest period of peace ever here in Europe, and we should be very proud of this. And it was because they took the toys from the bad guys, and the toys were made of steel, and iron is essential for it. And so that's why here there are 3 iron behind this. So that's why I say no iron, no weapons, no war. And I want to say thank you very much.